Assalamualaikum everyone and a very good day to all. In this video, we shall learn about data rate limit and the performance of data transmission. We will see how many bits per second we can send with the available channel and the data rate of noiseless and noisy channels are also examined and compared. Several channel measurements will be examined as well, including bandwidth, throughput, latency, and jitter. This is the last installment of a 3 parts video for chapter 3. Here is the table of contents for you to navigate through this video. Okay, let's start this video with data rate limits. This is a very important consideration in data communications where we want to see how fast we can send data in bits per second, okay, over a channel. So data rate, it depends on 3 factors. The bandwidth available, the level of the signals we use, the quality of the quality of the channel, which is it means the level of noise. There are 2 theoretical formulas that were developed to calculate the data rate. One is by Nyquist for a noiseless channel and another one is by Shannon for a noisy channel. For a noiseless channel, the Nyquist bitrate formula defines the theoretical maximum bitrate, where bitrate equals to 2 times bandwidth times log2 of L, which is the number of signal levels used to represent the data, and or you can use 2 times B, or the bandwidth, times log2 times 2 to the power of n, where n is the number of bits in a signal. So in other words, 2 to the power of n is also the number of signal levels, or L. So increasing the level of a signal reduces the reliability of the system, as the receiver must be sophisticated enough to distinguish between higher number of different levels. Although as we can see from the formula, we can think that given a specific bandwidth, we can have any bitrate we want by increasing the number of signal levels. The idea is theoretically correct, but there is a limit. When we increase the number of signal, like I said, we impose a burden on the receiver. So if the number of levels in a signal is just 2, the receiver can easily distinguish between a 0 and a 1. And if the level of signal is 64, the receiver must be very sophisticated to distinguish between 64 different levels. In other words, increasing the levels of a signal reduce the reliability of the system. In other words, Nyquist gives the upper bound for the bit rate, or basically the maximum bit rate of a transmission system by calculating the bit rate directly from the number of bits in a symbol or signal levels and the bandwidth of the system. The theoretical upper limit to the bit rate of a given channel or maximum bit rate may also be looked as the capacity of the channel. That means that the channel capacity is also measured in bits per second, because channel capacity is proportional to the analog bandwidth. Some people might call it digital bandwidth. Okay, so again, with the bit rate of a system, we increase with an increased number of signal level we use to denote a symbol, and a symbol can consist a single bit or n bits. Okay, so remember, as the number of level goes up, the spacing between the level decreases. So this will increase the probability of an error or the reliability. Okay, so the error will occur in the presence of transmission impairments. Let's do an example for noiseless channel. Consider a noiseless channel with a bandwidth of 3000 Hz transmitting a signal with 2 signal levels. Calculate the maximum bit rate. So you have the bandwidth and you have the signal level, which is 2. So you can calculate bit rate equals to 2 times 3000 times log2, 2 times 2. Okay, so with that you get 6000 bit per second. Again, another example, again, but this time you have 4 signal levels, meaning that for each level we send 2 bits. So with the same equation you can calculate, you get 2 times 3000 times log2, 4 times 4. Okay, so you'll get 12,000 bit per second. So what happens if you need to find the signal levels and the bit rate is given? So you need to send 265 kilobit per second over a noiseless channel. That means that we are using the Nyquist bitrate formula with a bandwidth of 20 kilohertz. So how many signal levels do we need? Okay, you already know the equation, okay, which is 2 times b times log 2l, and bitrate is 265 kilobit per second. And just substitute that into the equation, the bandwidth into the equation, and can solve for for L, where log 2L equals to 6.625 and L equals to 98.7. But you have to beware, this result is not a power of 2, so we need to either increase the number of levels or reduce the bit rate. So if we increase it, it will become 128 levels and the bit rate is 280 kilobit per second. Whereas if you reduce it, you'll get 64 levels and the bit rate is 240 kilobit per second. Depends on the requirement of your system. Okay, because you need to make sure that the level is in the power of 2. Of course, in reality, we cannot have a noiseless channel. The channel is always noisy. In 1944, Claude Shannon introduced a formula called the Shannon capacity. This formula is to determine the theoretical highest data rate for a noisy channel. In this formula, we can see that capacity equals to B times log 2 in the bracket 1 plus SNR, where B is the bandwidth of the channel, SNR is the signal to noise ratio, and capacity is the capacity of the channel in bits per second. Note that in Shannon formula, there is no indication of the signal level, which means that no matter how many levels we have, we cannot achieve a data rate higher than the capacity of the channel. In other words, the formula defines a characteristics of the channel, not the method of transmission. Let's do an example for a noisy channel. Consider an extreme noisy channel in which the value of the signal to noise ratio, or the SNR, is almost zero. In other words, the noise is so strong that the signal is faint. Calculate the capacity for this channel. So C equals to B times log 2 in the bracket 1 plus SNR, and we assume that SNR equals to 0 as the noise is too strong. And we will get, if you do log 2 1, you'll get 0. So B times 0 equals to 0. That means that the capacity of this channel is 0 regardless of the bandwidth. In other words, we cannot receive any data through this channel. Let's do another example. Calculate the theoretical highest bit rate of a regular telephone line. And this telephone line has a bandwidth of 3000, just from 300 to 3300 Hertz, and assigned for data communications. The SNR given is 3162. So we can calculate the capacity of this channel using previous equation. C equals to B times log 2 in the bracket 1 plus SNR. So the SNR becomes plus 1. So you just multiply and plug in all the information given and you get 34,860 bit per second. Okay, this means that the highest bit rate for a telephone line typically is 34.86 kilobit per second. So if you want to send data faster than this, you could either increase the bandwidth of the line or improve the signal to noise ratio. Let's do last example for noisy channel. We have SNR given, but in this case we are given in decibel, the SNR dB 36, and the channel bandwidth is 2 megahertz. Okay, so you can calculate the channel capacity. Again, we already know all the information to find the SNR dB. With SNR dB, as I given you previously, SNR dB equals to 10 log 10 SNR. Okay, so we already know the SNR dB. You can find the SNR. From the SNR, you can calculate the channel. So here, if you inverse it and get the SNR equals to 3981. Okay, make sure you know how to calculate this on your calculator. And the capacity equals to B times log 2 1 plus SNR. So the B is a given, which is 2 megahertz. Okay, and multiply with log 2, and SNR plus 1 is 3982, so you get 24 megabit per second. In practice, we actually need to use both methods, Nyquist and also Shannon capacity, to find the limits and the signal levels. So let us see with an example. um, we have a channel with a 1 megahertz bandwidth. The SNR for this channel is 63. What are the appropriate bitrate and the signal level? So you are given with the bandwidth, you are given with the SNR, you can calculate easily using Shannon formula to find the upper limit first. Okay, so B equals multiply with log 2, 1 plus SNR, you get basically 6 megabit per second. And from there, you can find your signal level, okay, from the 6 megabit per second. But actually, if you want, you should always use the better performance with something lower than the upper limit, because remember that Shannon formula is the maximum, theoretically, the maximum bit rate. So we can always make it lower. Okay, so for example, in this case, we take it as 4 megabit per second. And now we can use the Nyquist formula to find the number of signal levels. Okay, 4 megabit per second equals to 2 times the bandwidth, okay, which is 1 megahertz, and log 2L, and you want to find L. If you rearranged it and find the inverse of log 2, you'll get L equals to 4. Okay, so make sure you know how to do this on your calculator again. I keep reminding you, but you have to make sure that you know how to do this. Okay. Up until now, we have discussed the tools of transmitting data signals over network, and we saw how the data behave. But one of the important issue in networking is the performance of the network, like how good it is. We need to discuss the quality of service and overall measurement of network performance. And in this section, I will introduce you some of the terms that we will definitely use again and again in the future chapters. So the first one is the bandwidth. One characteristic that measures network performance is bandwidth. However, the term can be used in two different contexts with two different measuring values, either bandwidth in hertz and bandwidth in bits per second. Okay, bandwidth in hertz, we have discussed this concept. Basically, it is the range of frequencies contained in a composite signal, or the range of frequencies a channel can pass. For example, we can say the bandwidth of a subscriber telephone line is 4 kilohertz. Okay, and bandwidth in bits per second, the term bandwidth in bits per second that a channel or a link or even a network can transmit. Okay, so that is the number of bits per second. For example, one can say the bandwidth of a fast Ethernet network or the link in this network is a maximum of 100 megabit per second. That means that this network can send 100 bit per second. Okay, the relationship between these two, there is an explicit relationship between them. Okay, basically an increase in bandwidth in hertz means an increase in bandwidth in bits per second, and the relationship depends on whether we have baseband transmission or transmission with modulation, which is the broadband, if you remember, and we will discuss this further on, inshallah. In networking also, we need to know about the throughput. Okay, throughput is the measure of how fast we can actually send data through a network. Although at first glance, bandwidth in bits per second and throughput may seem the same, but they are actually different. Okay, a link may have a bandwidth of b bit per second, but we can only send t bit per second through this link, with t is always less than the bandwidth. In other words, the bandwidth is a potential measurement of a link, and the throughput is the actual measurement of how fast we can send data. Okay, so like again, give another example. We may have a link with a bandwidth of 1 megabit per second, but the device connected to the end of the link may handle only, let's say, only 200 kilobit per second. So that is much lesser, right? So this means that we cannot send more than 200 kilobit per second through that link. Okay, another analogy is in a highway, we design to transmit 1,000 cars per minute from one point to another. However, if there is a congestion on the road, then the value of the car per minute will be reduced. For example, just now I said 1,000 cars per minute, maybe after congestion only 100 cars per minute. So the bandwidth is the 1,000 cars per minute, and the throughput is the 100 cars per minute. And then we have latency, or sometimes people call it delay. The latency or delay defines how long it takes for an entire message to completely arrive at the destination from the time the first bit is sent out from the source. We can say that latency is made up of four components, which is the propagation time, transmission time, queuing time, and processing delay. So let's look closer into these components of latency or delay. The first one is the propagation time. Propagation time is the measure of the time required for a bit to travel from the source to the destination. And the propagation time is calculated by dividing the distance by the propagation speed. So in this case, if you know the distance and you know the speed, then you can get the propagation time. Propagation speed of electromagnetic signals depends on the medium and on the frequency of the signal itself. For example, in a vacuum, light is propagated with a speed of 3 times 10 to the power of 8, but it is much lower in air and even lower in cable. Okay, so typically I will give you 2 times 10 to the power of 8, but with different medium, we have different speed. And then we have transmission time. Transmission time is the time at which all the bits in a message arrive at the destination, meaning that the difference in arrival time of first and the last bit. Okay, so the transmission time will be looked at only at the receiver side. Okay, so the arrival of the first bit at the receiver side and also the last bit at the arrival side. I mean the receiver side. Okay, and the transmission time of a message depends on the size of the message and the bandwidth of the channel. That means that if you have a large size of a message, the packet is so big, then the transmission time will be greater. And same with bandwidth. If you have a great bandwidth, then it will definitely reduce the transmission time. But if you have a small bandwidth, then it will not help with the transmission time. Let's go to the other two components of latency, which is the queuing time and the processing delay. Queuing time is the time needed for each intermediate or end device to hold the message before it can be processed. Okay, it is not a fixed factor. It will change depending on the load on the network. If there's a heavy traffic, then the queuing time will be increased. An intermediate device such as a router, it queues the arrived messages and processes them one by one. So if there are a lot more messages, then each message will have to wait. The processing delay is the time required for a router or a destination host to receive a packet from its input port, removes the header, perform an error detection procedure, and deliver the packet to the output port. Okay, so in this course particularly, I will be typically use negligible time for queuing time and processing delay. You would not need to know how to calculate them unless if you go deeper into the each particular cases of a router, for example. But in this course will be assumed to be negligible. So basically, the queuing time is the time a packet waits in input and output queues in a router, and the processing delay is the time required to process a packet in a router or a destination host. Okay, let's see the last two performance metrics. We have bandwidth delay product and jitter. In bandwidth delay product, it defines the number of bits that can fill the link. The product of bandwidth and delay, which are also the two performance metrics of a link that we saw just now. So you can just imagine we have like a pipe or a column with the delay is the analogy for the length, okay, and volume is the bandwidth delay product, and the cross section is the bandwidth, as you can see in this small figure here. And then let's look at the figure on the left at the top. Okay, let's just imagine that we have two cases. Okay, the first case is on the left is when we are filling the link with bits for case 1. Okay, Let us assume that we have a link with a bandwidth of 1 bit per second. I know this is unrealistic, but this is just for example. We also assume that the delay of the link is 5 seconds, also unrealistic for demonstration purposes only. Okay, we want to see what bandwidth delay product means. Okay, so in this figure, we can see that the product or the bandwidth delay product is 1 times 5, which is the maximum number of bits that can fill the link. Okay, so there can be no more than 5 bits at any time on the link. Okay, let's see the case number 2 on the right, top right. Now assume that we have a bandwidth of 5 bits per second. This figure we can see that it can be a maximum of 25 bits on the line, which is 5 times 5. Okay, so if you have if you increase the number of the bandwidth, then definitely the bandwidth delay product will be increased as well. Same goes to the delay. If you increase the delay, then the bandwidth delay product will be increased. Okay, so these two cases show that the product is the number of bits that can fill in the link. Okay, this measurement is important if you need to send data in bursts and wait for the acknowledgement of each burst before sending the next one, because we want to use the maximum capability of the link. So we need to make sure the size of the burst is 2 times the product of bandwidth and delay. We need to fill up the full duplex channel in 2 directions, and the sender should send a burst of data, which is 2 times bandwidth times delay bits. The sender then waits for receiver acknowledgement for part of the burst before sending another burst. Okay, so the amount of 2 times the bandwidth times delay is the number of bits can be in transition at any time in a full duplex channel. Okay, let's see with jitter. Another performance issue is jitter. We can roughly say that jitter is a problem if different packets of data encounter different delays and the application using the data at the receiver side is time sensitive. For example, audio and video data. Okay, like for example, if the delay for the first packet is 20 millisecond and the second packet is 45 millisecond and the third is 40 millisecond, then the real-time application that uses the packet endures jitter. Okay, so with that, I think it's finished for this chapter. Before I end this video, please let me know how is your understanding on this topic throughout this video so far at this link. Your participation is highly appreciated. If you have any questions or comments, please let me know. Thank you and see you on the next video.